In this video, we're going to be learning about the first of three trends or patterns that is observable within the elements of the periodic table, which is what we call the atomic radius. Now, the term radius is identical to the term that is used in mathematics because we can actually measure, assuming that you could actually see atoms, the distance between the nucleus, which is the center of the atom here, and if we measure the distance between the nucleus and the outermost electrons that we find in the valence shell, this would give us the atomic radius. So in this case, we're going to use hydrogen as an example, and we're going to use the Bohr-Rutherford model of the atom. So here is hydrogen's nucleus. Hydrogen is atomic number 1, which means that it has one proton, and then in the single shell that it has, which by default is its valence shell, it has one electron. So the distance from the center of hydrogen's nucleus to its valence electron is what we refer to as atomic radius. Now, in this video, we want to explain what happens when we go down the periodic table, so from hydrogen downward, and what happens when we move from the left side to the right side of the periodic table. Now, from this diagram, it should be obvious, but we want to look at the reason why we see these patterns. So what we're going to do is compare the atomic radius by looking at the Bohr-Rutherford structures of the elements in the alkali metals. So if we start with hydrogen, which we've already drawn, hydrogen has one electron in the first shell. But if we were to draw lithium has 3 electrons because it's element number 3, meaning that its first electron shell is full, and then its third electron exists in the outer shell right here. Now, if we, assuming that these circles are concentric and of identical size, we can see that if we measure the atomic radius of lithium, we can see that it is clearly greater than the atomic radius of hydrogen, simply because the second shell is a greater distance away from the center of the nucleus compared to the first shell. Then, if we do the same thing with sodium for an even more extreme example, here is sodium's nucleus. We have the first shell for sodium, which has 2 electrons. The second shell is completely filled with valence electrons like this, and because sodium is atomic number 11, we can put a third shell out here for the final valence electron, and if we measure the distance between the center of sodium's nucleus and the outermost shell, we can see that as we go from hydrogen to lithium to sodium, we can see that atomic radius is increasing as we go downwards on the periodic table, because as we go lower on the periodic table, each time we go to the next period, we add another electron shell. So the farther down the period we go, the more shells the element is going to have, and therefore when we measure the distance between the valence electrons and the nucleus, the farther down the periodic table we go, the farther those electrons are from the nucleus, and this is why atomic radius, which we will label as AR, increases as we go down the periodic table. We can also look at and try and justify the trend of why we see a decrease in atomic radius as we move from left to right. So here we can see, both in terms of the actual measurements that are given here and in terms of the size of the radii themselves, that the atomic radius is decreasing as it goes from left to right, or the opposite is also true. We can say that atomic radius increases when we go right to left. Now, why exactly is this? Well, what we're going to do is we are going to write the atomic numbers for each of the elements in the second period. So lithium is 3, beryllium is 4, boron is 5, carbon is 6, nitrogen is 7, oxygen is 8, fluorine is 9, and neon is 10. Now, if we remember what the atomic number represents, the atomic number also represents the number of protons, and we know that protons are the positively charged component of an atom. Now, what does this have to do with anything? Well, if we compare lithium and beryllium, for example, let's just write those two elements next to each other. So here is lithium, which has 2 electrons on its inner shell and 1 electron in its valence shell, and lithium has 3 protons. That gives lithium a charge of positive 3 in its nucleus. Of course, lithium, the element, has a charge of 0 because the number of protons is equal to the number of electrons. But when we look specifically at the nucleus, lithium has a charge of positive 3. Now, if we do the same measurement with beryllium, beryllium is atomic number 4, meaning that it has 4 protons, so its nuclear charge is going to be positive 4. Now, even though beryllium has 2 more electrons, remember that opposites attract, meaning that electrons that are negatively charged will naturally attract to the protons within the element's nucleus, and therefore, if beryllium has a charge of positive 4, this nucleus has a greater ability to attract electrons than a nucleus with a charge of positive 3. Now, if beryllium has a greater ability to attract electrons to it, that means that these electrons are going to move closer to the nucleus. So, as we go from left to right, the number of protons that each element has increases. And as the number of protons increases, the amount of positive charge that the nucleus has is also going to increase. Now, the simple question, does an element with more positive charge attract electrons more easily or less easily compared to an element with less positive charge? Well, the stronger the positive charge is, the more attractive the force is, and therefore, the more positive charge an element has, the more easily it is able to attract electrons and pull the valence shell closer to the nucleus, and that's why fluorine with 9 protons has a much smaller atomic radius than lithium with 3 protons, because its positive charge is able to pull its valence electrons closer, causing the atomic radius to decrease as a result. In the next video, we're going to look at the importance of atomic radius when we talk about ion formation, and that involves looking at the second periodic trend, something that we call ionization energy.